Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In our last lecture, we were discussing about various characterization techniques that are employed for characterizing transition metal carbene complexes, and in that regard what we had seen that various methods including that of X-ray diffraction as well as IR, Raman and carbon 13 NMR were extensively used in characterizing transition metal carbene complexes. The techniques that we discussed in our last lecture was single crystal X-ray diffraction, then IR, Raman spectroscopy as well as 13C NMR spectroscopy. And what we had seen that these techniques are extremely good at characterizing various transition metal carbene complexes of both types, that is the Fischer and the Strock types. X-ray gives a clear idea as to the transition metal carbene bond lengths, which would be a sort of multiply bonded and should have a very short distance. We had seen that reflected in the transition carbene bond length both in the Fischer type as well as the Strock type. Similarly, the infrared Raman spectroscopy was used in quantifying the electron richness of the carbene center by monitoring the stretching frequencies of the transition metal carbene which were trans to a NHC ligands. So, these threw light on the electron richness, of CR2 moiety bound to a transition metal. The bond length and the X-ray similarly gave ideas on the bond length, on the strength of the CR2 bond, like threw light on of CR2 transition metal CR2 bond that we had seen in terms of that being multiply bonded and shorter bond length. Similarly, we had also looked at the chemical shift in the carbon NMR, which was widespread. Chemical shift of carbon NMR was widespread, and that did not provide any indication as to the reactivity of the type of the carbenes that are studied. So, of these three, even though the carbon 13 could characterize these moieties, but they did not provide any insight onto what kind of reactivity these carbene moiety would exhibit depending on the chemical shift. Whereas IR or Raman studies clearly gave a method for quantification of the electron richness of the carbonic center as well as X-ray diffraction study by looking at the metal carbene bond length. We are also able to give insight as to the strength of this metal carbene bond as to with the multiple bond nature of this metal carbene bond leading to its greater strength. Now, we are going to continue this discussion in bit more detail, and we are going to look at another most powerful technique for characterization of this metal carbene moiety, and that is from the perspective of proton NMR. Now, proton NMR is a very common ubiquitous tool that is used for characterization of all compounds, and this is no different in case of organometallic compounds too. So, they provide a very useful and effective method for characterizing these organometallic compounds, and we are going to be discussing this the effective use of proton NMR in providing insight onto the metal carbene moiety. So, this is from the perspective of how does proton NMR can be effectively used for characterizing metal carbene complexes. For example, proton NMR give the proof of multiply bonded nature of metal carbene moiety as well as multiply bonded nature of CX double bond character. And the same can be seen from the proton NMR of a Fischer carbene complex, particularly for pentacarbonyl, chromium, C O methyl. Now, this geometry is called a trans geometry, trans with respect to the 2-methyl, and in the solid state, in the solid state it exclusively exists in the trans form. Transform prevail, and as a result, if one were to record proton NMR of these compounds, there are two methyl resonances, two types of methyl resonances. One is methyl, another is OMe, and for OMe there is only a single resonance in the trans form, whereas in solution, this compound exists in the both cis and the trans form, and that equilibrium can be given as this. Now, this is the cis form. So, in solution at minus 40 degree centigrade, both cis and trans forms exist, and as a result there are 4 proton NMR signals, resulting in 4 proton NMR signals. Two from the cis form and the 2 from the trans form, whereas in the solid state where only trans form exists, that would exhibit only 2 proton NMR signals. If one were to record NMR of it, but in solution they sort of interchange between cis and trans. Now, this is a very important observation, that in solid state you have only trans form exclusively, whereas in solution you have both the forms cis and trans. What does that imply is that implies that there is a rotation along the CO bond. Now, this rotation of the CO bond would allow the interconversion between cis and trans, and this rotation is supposedly quite fast, because at minus 40 only you can see the interconversion happening. So, this rotation happens at very fast time scale, and that is why you have to really go down at temperature of minus 40 to be able to slow the rate of conversion between the cis and the trans form. And higher temperature, owing to very rapid exchange, a coalescence is observed. Coalescence of is observed at high temperature, and one can sort of estimate the activation barrier for this exchange, which is about 52 kilojoule per mole for the rotation along the CO bond, for the rotation along CO bond. So, what it proton NMR provides a useful insight in terms of the ability of the CO bond to rotate by looking at the spectroscopic signature, and this is something which is unique to proton NMR spectroscopy and can not be observed by other spectroscopic method that we had discussed in the last lecture. So, let us sort of study this rotation in a bit more detail. For example, in the nitrogen analog or variant of this Fischer carbene complex, particularly where the rotation is not very fast. For example, in this compound where pentacarbonyl chromium methyl with N-Me2, this rotational barrier is high, and the rotation is means very slow. The rotational barrier as a result, these methyl groups are non-equivalent, and which gives rise to three methyl signals at room temperature. So, these three comes from one of these and two of the N methyl. All three are inequivalent because the rotational barrier is high, and that leads to observation of three different signals at room temperature. Now, what one sees is the fact that if the C heteroatom rotation barrier is increased, then the non-equivalent methyl groups or the protons show up, and that results in inequivalent spectrum that we observe. Now, in case of Schrock carbene, for example, Cp tantalum, methyl, complex. Okay. Now, this CMCR2 is very rigid. This is rigid owing to to multiple bonding nature. As a result, non-equivalent non-equivalent CH2 protons observed up to 100 degrees centigrade. So, it shows that where there is multiple bonded carbene to tantalum, the rotation is not really possible. As a result, these two hydrogens are inequivalent, not equivalent, and this can be observed from proton NMR, and this non-equivalency exists up to a very high temperature of 100 degree centigrade. So, what we are seeing that proton NMR is providing some extremely useful insight about the dynamics of these carbene compounds in solution, particularly with respect to the metal heteroatom rotation, or with respect to the metal carbonic carbon rotation by looking at the equivalence or non-equivalent nature of the substituents on the carbonic carbon or of that on the heteroatom. So, this it provides a very useful method for getting an insight on the dynamics of these transition metal organometallic complexes using proton NMR spectroscopy. Now, with that we are going to move on to another important aspect of transition metal carbene chemistry, and this is with regard to reactivity of transition metal carbene complexes. Now, as mentioned in our previous discussion, that transition metal carbene complexes can be classified into two types: Fischer carbene as well as the Schrock carbenes, and both of these carbenes have metal carbene multiple bonding character, and however their interaction with the metal is different. For example, for Fischer carbene, it is a singlet carbene species which interact with the transition metal, whereas for the Schrock carbene, a triplet carbenic species interact with the transition metal using the same or similar metal to ligand and ligand to metal kind of bonding. Now, our analysis of transition metal carbene interaction, we had seen that owing to this type of metal ligand metal type of bonding that occurs for singlet Fischer carbene as well as for triplet Schrock carbene, there is a significant amount of difference in reactivity observed for these complexes, and they kind of behave in a very different fashion because of their different reactivity that arise because of their different way of interacting with the transition metal. Now, in this few minutes now, we are going to look at some of the examples of differential reactivity that this Fischer and Schrock carbene exhibit. For example, Fischer carbene is electrophilic in nature and reacts with a variety of nucleophiles. For example, for this chromium C OMe methyl reacting with C2H5NH2 gives methanol, particularly from the amine protonating the O-methoxy, and then give this corresponding CNH C2H5 carbene complex. So, what we see over here that O-methoxy has been protonated by this amine to release methanol, and this complex of the Fischer carbene is observed. Similarly, other nucleophile like phenyllithium also works reacts analogously. For example, for this pentacarbonyl tungsten C pH OMe complex reacting with phenyllithium at minus 78 degrees centigrade undergoes the attack of the phenyl moiety onto the positive carbon side to give the transition state something like pentacarbonyl tungsten C pH minus which in presence of acid eliminates methanol at very low temperature of minus 78 degrees centigrade to give the following tungsten C pH carbene complex. Now, what is important to remember over here that the Fischer carbene reacts with a variety of nucleophile, and that this attack arises from the carbonic center being partially positively charged, and that is because of the carbene to metal sigma donation cannot be matched by metal to carbene pi back donation. As a result, there is always a positive charge on the carbene which is the reason for the nucleophile attacking the carbonic center. So, this is a very important feature of Fischer carbene, that because of the bonding and the way it shows that the carbon is slightly positively charged, and that allows it to react with variety of nucleophiles the way it is shown over here. Similarly, carbenes can stabilize carbon ions. Carbon ion formed upon deprotonation Okay. Now, this is illustrated by very nice example over here. CO5 chromium C OMe methyl in presence of base CH3ONa and deuterated methanol CH3OD, what is observed that formation of CO5 chromium COMe CD3 is formed, which indicates that there is accumulation of deuterium at this methyl moiety, and that happens because this methyl gets deprotonated to make a carbon ion which is stabilized by the carbene moiety, for example, in presence of a base. This methyl gets deprotonated to give methanol, and the corresponding carbon ion this carbon ion is then stabilized by resonance to in this canonical form, and this, when treated with CH3OD, he protonates or puts deuterium on this methyl moiety, and after several such species it gives CdO3. So, what we have done is that in the that the carbon ion which is formed by the deprotonation of the methyl moiety is stabilized by the carbene, and that is because of the electron deficient nature of the carbonic carbon. Now, let me summarize what has been taught in this lecture. We have looked at proton NMR as a useful characterization technique to gain insight in the carbene metal complexes, particularly that provides insight into carbene metal bond rotation as well as CO carbene heteroatom bond rotation, and leading to different kind of resonances, equivalency and non-equivalency of resonances, leading to different kind of cis or transforms of the carbonic structure. We have also looked at differential reactivity arising from the nature of charge accumulated on the carbonic carbon for Fischer and the carbene Schrock carbene complexes, and for the Fischer one we had looked at the nucleophilic addition at the carbonic center with various nucleophile, and also we have seen that Fischer carbene can stabilize carbon ions forms upon deprotonation, and this was proved using isotopic experiment where one sees accumulation proton deuterium exchange in form of the example given over here. So, with this I conclude this lecture on characterizations of transition metal carbene complexes, and we are going to discuss more about the reactivity of transition metal carbene complexes in the forthcoming lecture, which will deal about differential reactivity of both Fischer and Schrock carbene complexes. So, till that time, goodbye, and I look forward to seeing you in the next lecture. Thank you.